Okay, so the second and last chapter we're going to do in 222 here is chapter 13, and it's chemical kinetics. So this is all about chemical reactions and how fast they're going, and a rough idea, eventually we'll get there, of kind of the energy landscape of these reactions and what we can kind of infer from them. And so the first thing I want to talk about is the kinetic theory of chemical reactions. So it's also known as collision theory. And what it is the idea that molecules have to touch each other for a reaction to happen. If I have two reactants, they're not going to just magically teleport into products. They have to come in contact. Collisions have to occur. And so one joke I like to tell about this, and I'm sure I'll get the usual response from an empty room that I do with a full one, but one example of a chemical reaction with collision theory would be how you make an SUV. To make an SUV, you have two Kias, and you have to smash them together, and you have an SUV. That's how everyone knows that's how you make an SUV, right? That's just common knowledge. Now you have to do it right. You have to have front of one Kia into the back of the other. If you don't do that, if you go like front or back to back, you get something else. Front to front, you get yard art. That's just a fact. You go back to back, you get a cool thing that can drive either direction. So you can go forward, backward, you can steer everywhere, but it's not an SUV. So orientation is important, and collisions with enough energy are important. You can't just tap bumpers. You've got to really crash them into each other. You got to get into that crumple zone, all right? So you have to have enough energy in this collision to cause the atoms to rearrange. They've really got to smack into each other. They don't just tap and bump off. Now, how much energy is enough energy? Well, that depends on the reaction. That depends on the reactants, so on and so forth. What's the correct orientation? Same deal. So you might get different reactions depending on what parts of molecules bump into each other with enough energy. And so what this does is it kind of gives us three factors for what is going on with a reaction. First is the number of collisions. The more collisions we have, the more likely we're going to get the one that causes the reaction. So that's going to favor our reaction happening faster. The second thing is strength of collisions. If they're not hitting hard enough, they're just tapping, no reaction. But boom, if they crash into each other, you get a reaction. So they have to be strong enough. And then orientation, and this some reactions is basically like any bump works. Some of them it has to be one part of one molecule hitting another part of the other molecule very specifically. And so orientation can be very important as well. But you know, the more of a window there is in terms of orientation, the easier it is to make the reaction happen, and the more quickly it'll happen. All right. So this kind of will guide us in the next topic. We're going to talk about reaction rate quite a bit for the next several videos. But just a very brief introduction to it here. This is how fast a reaction proceeds. So this is how quickly is my reaction happening? How fast are my products forming? How fast are my reactants going away? So I start out, I've got all reactants, and eventually over time I start making products, those reactants go away. How fast is that happening? For example, a combustion reaction, you take something like coal, which is just carbon, and you light it on fire. You make CO2, you just make CO2, there's no hydrogen on there, so no water. All right, so it reacts with the oxygen, makes CO2, happens very quickly. Diamond is another form of carbon. That will also form CO2, but it will do it much, much more slowly. So a diamond isn't quite forever, it's just for longer than we're gonna be around. Because it will break down in oxygen and form CO2, but it's a very slow reaction rate. It happens very slowly, all right? So reaction rate's very important, especially for us chemists, because if I'm working in like a chemical factory or if I do some sort of synthetic thing, I don't want to be sitting there for 2 weeks. I would like it done in an hour. So my perspective and the approach I'm going to take is kind of like, how are we going to speed this up? Because I have a very strong chemist bias to this. I want things to get done quickly so I can move on with my life. You know, those shows aren't going to binge watch themselves, and it's not going to happen if I got to babysit this reaction for forever. So, you know, if I'm sitting there, I'm like, this is going slowly, you know, how could I increase a reaction rate? Well, if we look at, you know, kind of our three factors, number of collisions, I could do a couple things to increase those. I can up concentration of reactants. So I can increase concentration of reactants. That's going to give me more collisions between reactants, more opportunities for a reaction to happen, which means the dice are going to, more rolls of the dice, more I'm going to come up with products. All right. The other thing I can do, keep it stirred, keep everything well mixed, break up chunks if I'm dissolving solids, that type of thing. All that's going to help increase number of collisions. And then strength of collisions. That would be the next thing. Well, how do I increase strength of collisions? How do I make molecules move faster? We talked about a certain physical property that's directly tied to the velocity of a molecule. Definitely talk about it in the gas chapter if you had my class. So the answer is you heat it up. Higher temperature equals higher molecular velocity on average equals stronger collisions. All right. We're gonna take it out of the 5 mile an hour parking lot and we're gonna put it on the 65 mile an hour interstate. All right. That's what we're gonna do. And that's gonna give us stronger collisions. And then the third one is orientation of collisions. That's actually very hard. Like I can't control the orientation of these collisions. It's totally random. But if you ever use a catalyst, that'll help a reaction proceed more quickly. And there's a few different avenues a catalyst can take, and this is one of them, is it'll actually help control orientation of these collisions. It'll hold on to molecules, like a lot of enzymes, which are protein-based catalysts, do this. So it's not super uncommon. So how do I increase my reaction rate? Keep it stirred, keep it mixed, heat it up, make sure I've got good concentrations of reactants. If I don't like the speed it's going, maybe I can add more. And all of that will increase my reaction rate. So from a chemistry perspective, that's what I do. That's how we apply the kinetic theory of reactions to it. I kind of put it all together. All right, so there's gonna be a lot of math in this chapter. This is kind of a very introductory overview. So messing around with concentrations, messing around with temperature. We're gonna talk about those factors independently in different videos. We're also gonna look at the change of concentration over time, things like that. So time is also a variable in these. Reaction rate is going to vary with time, and we'll talk about why. All right, so buckle up. This is a 2-week chapter, so don't feel like you have to power through it all in 1 week, but do make sure as you go through it piece by piece, you understand what's going on. A lot of it's going to build on itself, so hang in there.